So yes, I met Ryan a number of years ago when I was actually finishing up my peptide certification at the A4M, American Academy of Anti-Aging Medicine. And that was actually the first peptide certification that was launched by A4M. And that was the only one in existence in terms of really formally training doctors on peptides. And Ryan was one of the executives at TaylorMade Compounding Pharmacy, which is at that time the premier pharmacy that was offering peptides. And and I had been on peptides myself, and actually working with another gentleman, his name is Bill Lawrence, for utilizing peptides, especially from Russia, and noticing definitely changes in my own physiology, and doing telomere testing, and that showing significant improvements and so forth. And then, met back up with Ryan when he created his company that was focused on methylation and epigenetic testing, which was a much more accurate measurement of, let's say, life expectancy and health and all of that stuff. So was very pleased to do a test with him, and it actually showed me that what I've been doing over the years was actually very positive, because the difference between my chronological age and biological age was quite significant. So the path that I was on was a very positive one. So I'll let Ryan kind of dig into it and give his background and tell us all about the company.
Yeah, thank you so much, Dr. Carter. I appreciate the introduction. And yeah, thank you everyone for having me again. I gave a version of this talk yesterday, and I see some familiar names. So I hope that going back over this information isn't too much of a drag for some of you. But I'm always excited to talk about this topic where we're sort of talking about sort of aging as a disease. And we'll go into that a little bit more. But just to give a little bit of background on who I am and who our company is, TruDiagnostic is still a relatively young company. We started doing commercial tests in July of 2020. But in that time, we've done a lot of these types of age diagnostic tests. And so much so that we built one of the largest private epigenetic databases in the world to really, create the Rosetta Stone of how to interpret these new biomarker marks. And so what we're doing today, what we'll talk about today, is really the main application that we use this for currently, which is in age diagnostics. And we're doing a lot of research to try and push this forward, to learn a little bit more about the aging process, and really try and treat aging from a fundamental concept. And so as I did yesterday, I want to start off with just some questions to sort of help orient you all. And really the first question is definitely a personal one, but it's a big question. And that is, how long do you think you'll live? And I know that Zoom has some of the ways that you can sort of raise your hand. And so I'll just ask this a little bit rhetorically. But, whenever I ask this in lecture halls, I always see people who have, really, I would say, high expectations of how long they'll live. I would say in most of the areas that I'm at, I see, over 40% of the room say that they're going to live over 105, which is great. I hope that everyone I'm talking to does live that long. But unfortunately, I think that that's not necessarily the case. And so the US life expectancy continues to go up. Obviously, we might have had a blip there in 2020 for COVID, but unfortunately, Americans are really bad at guessing how long they're going to live. The majority are actually very incorrect, missing it by several years or even decades. And so unfortunately, we've not been great at guessing this, because there's a lot of factors which are involved in this, the predisposition to disease being number one of that. And so I always usually say that this is something we want to change. We want to increase life expectancy significantly by treating the aging process, and think that we definitely can. But along with that, we always ask the secondary question of how long do you want to live? And this one is a lot more complex, because, whenever I see that 40% raise their hand, I do not see 40% raise their hand for 105 for this question. And I would say that mimics what we see in the clinical literature as well. This was a study that was recently done in 2021 on a Norwegian population, and it said that the average person wanted to live to the age of 91. And so that, first off, that's 12 years longer than most of us are going to actually live due to these life expectancies. And so we want to know how we can close that gap. How can we get everyone to live to 91? But beyond that, how can we even do better? How can we get people to live longer and happier lives so that they want to live as long as they can? And so the considerations which go into this are some factors that we want to define right off the bat, which is what is lifespan and what is health span? And I think everyone knows what lifespan is, obviously how long you're living, but health span is equally important as we consider how we want to live. Quality of life does diminish as we get older. So how can we increase our health span across time? And, in the Middle Ages, this was something that we didn't really have to worry about. Whenever we usually passed away, usually it was due to something that happened rather immediately, some type of traumatic event or a virus or some type of other pathogen. But now, for the first time in history, our lifespans are getting longer, but our health spans are actually diminishing. So we're living the majority of our lives being ill or sick. And so this is definitely something we need to change. But the question is, how do we do it? And that's what I want to introduce today, is hopefully a tool which will allow us to treat aging as a disease. And so I know that aging as a disease might not be something that many of you might sort of think right off the bat, but hopefully I'll persuade you that this is the case. And I think one of the best arguments for aging as a disease currently is that aging is the #1 risk factor for almost every chronic disease and death. If you can think of a chronic disease, age is usually the #1 risk factor. And beyond that, I always usually use these thought experiments, is that there's a reason that people in their 30s and are not coming out with the same amount of illnesses as people in their 60s. Over 80% of people over the age of 65 will have some type of chronic disease diagnosis. And again, that just doesn't happen when we're younger. And so this idea of biological age, which we'll talk about a little bit later, is one of the ways we can definitely affect this. If everyone in the world were 7 years younger biologically, or the age of their body was 7 years younger than they are chronologically, which is the number of sort of candles on your birthday cake, we would be able to cut disease in half. 50% of people would no longer be sick if everyone were 7 years younger biologically. And so we really want, first off, to change that, but also we need a way to measure it. And just to give you some additional statistics, if everyone in the world were to increase everyone in the United States were to increase their life expectancy just by a single year, we could save over $256 billion in the United States on healthcare spending, and over $8.8 trillion in economic impact if we increase that by 10 years. And so we definitely believe that aging is a disease and one that can be treated. But in order to do that, we have to know how to measure it. And that's where we come into some issues. And so I always like to introduce this topic of the phenotypic variation. And this is something that you are all probably familiar with, despite its relatively complex name. And this is, I always liken it to us knowing people in their 70s who look like they're in their 50s, people who should look and behave a lot older, but who are in the peak health, and then vice versa, those people who are younger but are behaving more like they're in their 70s or 80s. And this phenotypic variation is one of the biggest confounding factors for measuring the aging process. Chronological age is simply just not accurate enough for us to really use as a biomarker. And so the search for a better measurement of age has been happening for a long time. And that is really this history of biological age. And so this is the age of your body. And this is a much better way to measure where we're at on our lifespan. And this search for a biological age measurement has been happening even since the early 1900s, where they were doing really crude measurements, like telling you your biological age was your chronological age plus 1 year for every pack per day you smoked. So really, really crude measurements. Really in the 1980s, the American Federation of Aging Research formulated the following criteria for a biological age predictor. And first, it must be able to predict the rate of aging or where someone is across their lifespan. Secondarily, it must monitor a basic process that is underlying the aging process and not the effects of disease. And that's one of the most important and most difficult things to do. And that's because we know aging is the biggest risk factor for many chronic diseases, but we also know that disease actually accelerates that aging process. So sometimes it's very hard to tie those apart. In addition to that, we must be able to be tested repeatedly without harming the person, and it must work in humans as well as laboratory animals so that we can do testing before applying it to humans. And so really, unfortunately, in 2013, really no marker had fit all this criteria. But thankfully, in 2013, these epigenetic clocks were first created. And these epigenetic clocks are basically ways to tell the age of your body by looking at these epigenetic methylation markers. And we'll get into what that is in a minute. But I want to just provide a little bit of history of this measurement first. When this first came out in 2013 by Dr. Steve Horvath from UCLA, it really wasn't applied to health immediately. It was applied to things like dating DNA at crime scenes to see how old the suspect might be, or dating refugees from the Syrian refugee crisis to see if they were eligible for asylum, if they were adults or minors. And so this was used in a lot of different aspects in society, but it wasn't necessarily applied to health. And that was until they started to see that those people who had higher biological ages than their chronological ages were at significant risk of increased disease. And vice versa, those who were younger biologically than their chronological age tended to be prevented or have sort of lower risk factors for all these chronic disease. And so, this is a really big breakthrough. I think that Dr. Horvath, who created this first clock, will eventually be nominated for a Nobel Prize. I think it is an amazing breakthrough. And if there's one big takeaway from this talk, it is that this data that we're generating, this epigenetic methylation data, is going to revolutionize healthcare in almost every aspect of healthcare, everything from cardiology to immunology to oncology. The epigenetic methylation will change that. And so they actually even anticipate that epigenetic methylation will overtake blood testing in frequency over the next few years. And so before we dive more into these clocks, what they are and what they mean, I want to talk about what we're actually measuring, which ultimately are these epigenetic marks. And so many of you might not be familiar with this idea or term of epigenetics, but it is very, very important. And this is, epigenetics stands for above the genome, or changes that happen above the genome. And really, we can think about these changes to be on or off switches to our DNA. Every single cell in your body has the exact same DNA sequence, whether we're measuring your skin or your heart cells or your saliva or your brain, all the same DNA. However, as you know, those cells behave very, very differently. Our skin behaves very differently than our heart cells. And that's how we want it, so that each cell can have a specific action. And the way that it gets those sort of behaviors is by what DNA is turned on or off. And so those are epigenetic marks. Those marks which change how our DNA is expressed or turned on or turned off. And so the DNA is essentially the blueprint, but what actually is implemented is due all through these epigenetic marks. And there are a lot of different epigenetic marks that can occur. There are two main I would say methylation and histone modification marks, which really constitute the majority of what we're looking at. And so DNA methylation is essentially the off switch for your DNA. It is how your DNA is sort of turned off by blocking transcription of that DNA from then going into RNA, which creates peptides and proteins. And so alternatively, the histone modification is sort of the on switch. And that's basically like taking two oppositely charged magnets and pushing them together. You see this force repels. And when it repels, it opens up this DNA to be able to be transcribed by those proteins, which regulate the transcription machinery. And so think about DNA methylation as the off switch and histone modification as the on switch. For us and our purposes, the ability to measure DNA methylation is still relatively new. And we're now getting this data for the first time at really large scale. And so DNA methylation is really what we're measuring whenever we're trying to tell you how old your body is. And just to give you an idea of how much data there is here, every cell has a different epigenetic sequence and a different methylation-based sequence. And in each cell, there are over 29 million different locations we could look at and quantify. So this is a lot of data. And generally, this methylation is happening at a place we call these CPG regions, or these cytosine phosphate guanine regions, which are sort of, again, make up that DNA. And so that's where this is happening, and that's where we're looking to get this information. And so whenever we're doing an analysis of your epigenetic methylation, what we're really looking at is right around 900,000 of those locations in your genome. And at each of them, we're getting a percentage of methylation. Out of all the DNA copies we test, how often is that methylated? And generally, whenever you see that, we call this beta value. And generally, this is just a percentage. And the higher the percentage, that means the less expression of that DNA that we're getting. And the lower the percentage, the more expression of that DNA that we're getting. And so, so this all culminated, this idea of being able to look at our epigenetic methylation into this idea of biological age. And the way that it did this was basically by looking at some of these locations which are regularly and reliably changed with age. And so basically some of these methylation marks increase methylation, some decrease methylation, but by using computer learning and artificial intelligence, we can create these algorithms which can actually tell us how old your body is. And these are getting very, very accurate. Many of you might be familiar with previous molecular biomarkers for age, like telomeres. And these epigenetic clocks are significantly better than telomeres. I always point to this 2017 paper, which compared all these biological age predictors, and really epigenetic methylation comes out on top in a very significant way. And so the question is, what should biological age be used for? And at first, the first thing we want to do with these biological age tests is get an idea of where we're at, because those individuals who are aging faster than their chronological age are definitely going to be at increased risk. And those people who are aging slower than their chronological age are going to be protected. And so first, we want to get an idea of where individuals are going, but ultimately, we really want to know how to intervene with this molecule or with these molecules and change our aging rates. And so just to give you an idea of how this can be applied to disease, I always like to use this example of cancer and the predictive power of epigenetic aging in cancer. And so this shows that for every 1 year that we're older biologically than chronologically. So if a 50-year-old person takes this test and finds that their biological age is 51, they would have a 6% increased risk of cancer within the next 3 years and a 17% increased risk of dying of cancer over the next 5 years. And so this is directly connected to how our risk of developing cancer, but it's also connected to our risk of developing almost every chronic disease. And so this is an example of one of the reports we'll have coming out here soon, where you can actually take the information that we give you on your biological age and see how it's affecting your risk of almost every other chronic disease. And so, for instance, if you have history of breast cancer in your family, you can look at some of these marks and your aging marks to see how either protected or how you are more at risk from accelerated aging from almost any disease. And again, going back to this idea of aging as disease, aging is the biggest risk factor for almost everything that we're trying to avoid. And so by looking at where we're at, measuring it, and then trying to find out what reverses this metric, we can hopefully make major differences to disease outcomes, as well as just increasing lifespan and increasing that health span metric we talked about earlier. And so, as I mentioned before, there are many, many different ways we can use this epigenetic information. Even currently, we can do things like tell you how much you've smoked across an entire lifetime, how many heavy metals you've been exposed to. We can even actually predict when you're going to die with fairly good accuracy. And these things are already being incorporated into things like life insurance companies to see how long you might be able to live and what premium they should charge you. And so this is definitely something you should be aware of. And so for us at TruDiagnostic, we do mainly 4 different aging reports. And we do our overall biological age report, which can report on all the things that might have increased or decreased your score at baseline. We also do sort of your immune age with your immune cell subsets, which are able to tell you essentially how well your immune system is aging and how well your immune system is functioning at the moment. In addition to that, and we already sort of knocked it a little bit earlier, but we can do things like telomere length assessments to tell you how long your telomeres are as another biomarker of aging. And that is one that's correlated to some other events as well. And then probably my favorite, and what I want to really talk about today and focus on, is our report on, which is the pace of aging. So at this exact moment, what is your speedometer of aging? How fast are you aging on a biological per year basis? And so this can give us a lot of information about your aging process, how your immune system is aging, how your body is aging, what your current rate of aging is, and even your telomere length, which is a classical measurement that now we can do with this exact same testing. And so I really want to dive into this pace of aging for multiple reasons, but this pace of aging, again, is that instantaneous sort of speedometer for how fast you're aging. So if we take your measurement right now, how many biological years per year are you aging? And this is one of the things that increases as we get older. If you can look at that population level graph there on the right, you can see that as people get older chronologically, their rates of aging tend to increase. And this is something we really want to avoid. For anyone who is even slightly above 1 in this pace of aging, so even if you're aging at a rate of 1.01, you would actually increase your risk of death over the next 7 years by 56%, and you increase your risk of a chronic disease diagnosis in the next 7 years by 54%. And so this is definitely something we want to keep of below 1. And in order to do that, we want to keep this as low as possible for as long as possible. And right now, this is considered probably one of the best, if not the entirely best, algorithm out there to quantify the aging process. And so just to give you an idea of maybe some of the history of these clocks and why this is now one of the most exciting, these first clocks use these algorithms and methylation marks and trained these methylation marks to predict the chronological age of an individual. And so that it still worked well. And as I mentioned, I still think that Dr. Horvath will get nominated for Nobel Prize for this. But the problem with this is that the better that these clocks got at predicting someone's chronological age, the closer they got to just predicting someone's birth date, which is just something we could ask for, right? We already talked about the problem with just measuring chronological age, which is that, there are massively different phenotypes of aging in those same individuals of the same age. And so those are those first generation clocks. But those second generation clocks that we talk about, instead, we're not trained to predict the chronological age of a patient, but trained to predict biomarkers that we can measure in patients that traditionally change with the age. So things like cholesterol and leukocyte telomere length, and things like albumin levels or C-reactive protein. And those clocks were significantly better at predicting outcomes. Their hazard ratios for disease were even more predictive. And so these second and third generation clocks are what we're using now. But this Dunedin pace of aging marker is actually the first ever third generation clock. And that means that it's a longitudinal data set. And so really in 1972 in the University of Otago in New Zealand, started to work with Duke to collect information on really young children. And the idea here was that Duke wanted to basically measure these aging rates across these individuals' entire lifespans, from the moment they were born until the moment that they die. And so this began in 1972 with over 1,000 children at the age of 3. And really, this group has been followed almost every year now until 2018, where they were age 45. And currently, we're even following them again for an age of 51 follow-up, which is currently ongoing. And what happened with these patients is that every few years they would take many different blood-related biomarkers. This is a list of those 19 blood-related biomarkers that we sort of took throughout this study, and includes everything from lung spirometry metrics to kidney-related metrics to inflammatory markers. Even gum health was measured for these patients. And so with that, we were able to create this instantaneous rate of aging that was essentially been able to perform via those epigenetic methylation marks. And so we actually followed them up at age 45 and wanted to see what this rate of aging correlated to in terms of physical and phenotypic responses. And so this is one of my favorite things to show, because what we found is that this rate of aging can greatly predict the phenotypes and even the health span of people at age 45. And so as you can see here on this x-axis, you can see this rate of aging. And you can see that as people increase their rate of aging at age 45, they actually would have lower grip strength, lower muscle mass, and lower sarcopenia, or I should say higher sarcopenia. And so generally, they're going to be less able to move about the world. And this is the same actually with balance testing as well. We perform one-leg standing balance test, and generally the faster your rate of aging, the worse your performance on balance testing. So again, the faster your rate of aging, the worse you're going to be able to move. You're going to have less muscle mass and less muscle strength, and you're more likely to have things like falls, which might greatly impact your aging predisposition. We also see this with things like cognitive decline, where the faster your rate of aging, the lower IQ that you're going to have. With on average, these people who are aging at a rate of 2 biological years per year, having around 15 IQ points lower than those individuals who are aging at a rate of 1. We also see this with brain MRIs, where we see reduced cortical thickness with faster aging and reduced surface area with faster aging. And we even see this in one of my favorite things to show is this facial aging. So everyone that you see in this picture right now is the same chronological age. And these are real computer-generated images from pictures taken from this cohort. And so on the left, you can see who are the slowest aging members of the cohort. But on the right, at the same age of 45, you can see the fastest aging members of the cohort. And they look to be almost 20 or 30 years apart, because biologically they probably are. Some have been aging very, very slowly, while others have been aging very, very quickly. And so one of the reasons I love to show this algorithm is because these are all quality of life metrics. And so as we answer that question about how long we want to live, if we can increase, our ability to think, our ability to move, and even how we look aesthetically as we get older, then hopefully everyone will want to live longer. And by managing this, we can not only improve those phenotype outcomes, but also improve our lifespan and diminish the risk of disease. And so that's why we think aging is a disease and it should absolutely be treated like it. Unfortunately, there are a lot of things which can affect our aging, and we're starting to untangle all of these different predispositions. One of the things we found with the disease and pace of aging is that aging rates even start in young adulthood and can be affected by things like your family's social class or the event of polyvictimization you might have. But the good news is we also know that this can be changed. And so this is one of my favorite studies to show, which is they performed a 2-year study on caloric restriction, where they basically ate 11% caloric restriction, meaning that your basal metabolic rate plus the amount of activity that you do over the course of a day, if you just multiply that times 0.9, that's how many calories you could take in. And this has been one of the most well-validated interventions for longevity and health span that we've known for a long, long time. And what we saw in this group is that the rates of aging in those caloric restricted groups on the right age significantly lower than those people on the left via this rate of aging marker, as well as just traditional biological age markers. And so what we know is caloric restriction is one of the ways we can change this, but also these rate of aging markers respond to things that we already know are beneficial to longevity biology. And so this is one of my favorite algorithms, but hopefully can illustrate why this measurement is so helpful and why we should be taking it to really encounter what things change this aging process and then make these really broad scale recommendations. In addition to these rate of aging, we also do things like telomeres. And if you're familiar with telomeres already, you should know that this measurement of telomere length has some benefits over traditional telomere length testing. It definitely outperforms regular telomere length testing in terms of predicting time to death, time to coronary heart disease, and time to congestive heart failure. And it's got double the correlation value to age of traditional telomere length. So in our type of reporting, this is the type of report that you would get, where we tell you your telomere length as we can estimate it, where you stand in the population, and we can even estimate your age based on those telomere length factors. And so again, telomere length is not generally as important as biological age. Again, it's 2% of our differences in phenotypic aging versus these epigenetic clocks, which are 30. And so we're going to prioritize it a little bit less, but it's still an important piece of the aging picture. If you were to reset these epigenetic clocks, which you actually can do, you'd still see telomere length shortening, and vice versa. If you reset these telomeres to be continually long, you'd still see epigenetic aging. So two different processes in aging, both very, very important, and both are able to be quantified with our metric, which is really, really exciting. But in addition to that, as I mentioned, this will be applied to a lot of different diseases as well. And we're already doing this with some of our reporting too. We're actually able to report how likely you are to become obese based on some of these methylation marks. We can actually even predict diabetes. And actually our diabetes predictors are subclinical and can actually detect diabetes up to 7 years earlier than fasting insulin and HbA1c, which are sort of the classical measurements for diabetes. And so if you can have a 7-year head start on trying to reverse your type 2 diabetes and insulin sensitivity, I think almost everyone would say that they want to have that. And so it speaks to some of the precision and early diagnostic.
Ryan, I've got to ask a question on the insulin.
Sure. Yeah, definitely.
Is that using insulin using standard reference ranges, or is that really fine-tuning insulin in terms of its improved predictive?
Unfortunately, that is just with the traditional reference ranges of fasting insulin and HbA1c.
So I'll give you a story. Yesterday, I had someone, and their fasting insulin was 2.4, and LabCorp considered it out of whack. In fact, the person has extremely good diet and is very insulin sensitive. At one point, my fasting insulin was 1.3, and Dr. Carter said, well, you should run a C-peptide because it's so low. I ran a C-peptide, it's normal. Then I went on a sugar binge and my insulin went up, proving that my islet cells still work. So definitely. I think the ideal fasting insulin is somewhere between 1 and 3, not between 2.7 and 25.
Definitely. And I think that goes,
just a little sidebar,
No, you're absolutely correct. And you bring up a good point, which is, what is optimal versus what is reference or what is normal. And hopefully, by treating things like aging, we can really shift that idea of what's normal to really what is optimal, including optimal aging rates. And so again, I think that the idea is that these methylation marks are incredibly sensitive. They can be used in subclinical fashions.
But it's such a good it would be such a good way to validate the blood testing and vice versa.
Yeah.
Because we based our range, like white blood cell counts, on early mortality, 4,000 to 5,700. Standard of care varies all over the board, but 3,500 to 10,800. Mm-hmm. But 4,000 to 5,700 still is not optimal for perfect health. You want to be between 42 and 4,600. But then exactly. you got to look at the differential of that to get even more refined. So it would be really interesting to pair the two technologies.
Completely agree. And that's what's happening, I think, is these composite biomarkers, which take information from many different sources, are going to be the most applicable. But we're sort of in this epigenetic revolution for the first time ever and getting a lot of good data. And so I think I said this in my first presentation as well, but even just 2 weeks ago, they published a study from Sweden where they were actually able to now separate type 2 diabetes into 4 different subtypes, each with different risks associated with it and each with different recommended treatments associated with it. And so we're starting to get much more resolution by getting more molecular information, which are going to improve our diagnostics and as well as improve the way that we hopefully correct for some of these diseases as well. And so again, this epigenetic methylation is a way that hopefully we can improve both of those things. And as I mentioned earlier, we can also tell a lot of other interesting things. In addition to being able to predict disease, we can also look at a history of all of your exposures. And so really, these epigenetic methylation marks are also a log of almost everything you've been exposed to throughout your entire life. We can actually see, genetically, those people who have been descended from Holocaust victims or the Rwandan genocide based on the methylation marks they have in their DNA and are passed down from generation to generation. But we can also see a history of all of your exposures, including toxic exposures like heavy metals. And I heard, some talk of that when I joined the call this time. Hopefully we'll be able to have really good ways to look at your overall as well as your current heavy metal exposure and actually tell you which metals you've been exposed to with one simple and very easy test. And so we're definitely doing that. As I mentioned, the exposure we're going to be focused on at least first are going to be things like illicit drug use or particularly smoking and drinking, as we have really clear signals for what those are due to really large population data sets. And so for this to smoking, we know that that's one of the biggest things that can affect your epigenetic aging rate, for instance. It was one of the most detrimental things to aging, which is pretty informative. But even beyond that, we're now going to be able to do things like pharmacoepigenetics, where we can actually predict your response to things like metformin. Are you going to have a HbA1c reduction, or are you going to have side effects? We can actually predict that before you even actually ever take the drug. And so we're really excited about all the different implications. But ultimately, when it comes to aging, I think we're also really excited to talk about what changes these epigenetic clocks. And so that's really what I want to sort of end on, is going through a couple of these interventional trials, which have already happened, but mainly, there are things we know now which can change these epigenetic clocks, things like vitamin D or the Mediterranean diet or fitness and sleep and exercise regimens, which have been very, very well validated. But I also want to hopefully give you some hope as we end this call. If aging is a disease, I want to make sure that I give hope that we can actually treat and change that. And so a lot of the things I'll be talking about now are really a long way away from actually being implemented, but are still incredibly exciting. And so one of the first things I always want to reference is Altos Labs, which is a very new company, only sort of started up right around 4 months ago. But really funded as the biggest and most well-funded startup of all time. They gave this company over $3 billion to reverse aging and disease. And this is done by Jeff Bezos and Yuri Milner. And really, they're all focusing on using one type of treatment to reset these epigenetic clocks from really their age back to zero. And they're doing that via these things called Yamanaka factors. And so, this Dr. Yamanaka from Japan really won a Nobel Prize in 2012 for the ability to take cells from any part of your body, these somatic cells, as we call them, whether they're skin cells or hair cells, and use a combination of growth factors to actually turn those back into pluripotent stem cells, so cells that can become anything. And this was a really exciting development, but it became even more exciting when we started to use these epigenetic clocks and see that their ages were automatically reset to 0. And so even now, these things are being used in animal studies to reverse the aging process. This is an example from Dr. David Sinclair's lab at Harvard, where they actually took mice who had lost their vision due to age-related blindness, injected these Yamanaka factors, and were actually able to both reverse the epigenetic ages of these eyes, but in addition to that, they were able to restore vision in these blind mice. And so the ability to reset these epigenetic clocks back to 0 seemed to be accompanied with functional improvements in aging-related diseases. And now this has been done in not just mice, but also in skin cells that have now improved and reduced wrinkles, improved elastin, improved collagen. And so this is a huge area of research. Now there are 4 or 5 different companies who are trying to take this on, and it's another really exciting area of development. In addition to that, I always like to mention young plasma. And so many of you might have heard this. There are a couple pop culture references that incorporate this, but it all started with this study where they took a young mouse and an old mouse, and they actually hooked their vascular systems together. So the old mouse was using its heart to beat blood into the young mouse and vice versa. And whenever they did this, they found some really interesting things. So in particular, the old mouse started to rejuvenate. It actually had increased fur thickness and reduced gray fur, and improved cognition and improved motor function and muscle mass. But vice versa, and surprisingly so, the younger mouse also started to get older phenotypically. And so this was really interesting and really brought up this idea that maybe that there's some factors in young blood which might be able to regenerate old mice, and vice versa, there might be some factors in old blood which might cause aging for younger mice. And so this has brought this idea of young plasma treatments, where we can take plasma from younger individuals, in the case of humans, somewhere between the age of 18 and 22 years of age, infuse them into older individuals, and see phenotypic reduction, so improvements in all of these aging processes. Whenever they actually did this in mice, they were able to reduce these epigenetic age across 4 tissues by 54.2%, so major reductions. And again, just to give you some of that context, remember, if we reduced everyone's age by 7 years, we'd be able to cut disease in half. And so they're seeing 50% reductions. And again, if that can be applied to a human model, that can be very exciting for how we sort of behave and treat disease, as a population. And so really excited about this type of potential therapy as well. One of the other big therapies we're excited about is even rapamycin. Rapamycin has had at the lowest lifespan extension in animals to be 9% and could be up to 30%. In the case of dogs, for instance, it's more on that 30% line. And I actually give it to my dog as a way to increase its lifespan. As a Bernese Mountain Dog, they don't live that long, and any time with a loved pet is exciting. And so this is not just applied to human medicine, but almost every mammal as well. And so so hopefully those give us some things to be excited about. I know I don't have much time before I open up to questions, so I just really quickly want to go into some of our research that we've been doing, and we are doing a lot of research studies at the moment. We currently have over 30 trials underway, and 12 of those are looking at interventions, and we've already published some very unique findings. And so one of the things we looked at was what effect does COVID-19 have on these rates of aging? And so we actually published this with both collaborators at Cornell and Yale, and we actually saw that there was a very interesting split from these aging rates according to your actual chronologic age. We saw that people who were younger than 50 actually sort of had anti-aging effects with COVID-19, while people over 50 actually had epigenetic age worsening. And we think that's because obviously as we get older, our immune systems get worse. That's why obviously older individuals are recommended to get their vaccines first. And we think that as people age, their immune systems get worse and are unable to mount a response to correct from these type of pathogens and viruses. And while younger people under 50 are able to mount these responses, and when they do, they can actually improve their overall age. And so we definitely found that. We also looked at the effect of mRNA-based vaccines. And surprisingly, and probably nothing that I would say read into too much, but we saw actually anti-aging effects of the mRNA-based vaccines, and we don't actually think that that was an age reversal. We actually think it was just mitigated by some of those changes in the immune cells that we were seeing. But it's still an interesting finding nonetheless, and begs the question: Do vaccines help prime the immune system and maybe help reverse some of the aging-related changes we see in the immune system? So, in addition to that.
Ryan, Can check there. So with that, obviously that's a timed type scenario. So of course, what I'm finding, and a lot of doctors are finding, and of course I don't have a significant cohort of patients, but what I am finding in individuals who taken the vaccine, and generally it's 3, 4, 5 months out, 6 months, and where we're finding actually some negative efficacy, right?
Sure.
But I am finding lowered, especially CD8 levels in those individuals. So I guess the question would be, when you guys did the epigenetic testing, what was the time frame? Did you do it, month 1, month 2, month 3? Because that has yes, I would say that obviously the vaccine does have some enhancement, shall we say, of the antibody response. However, it's just not long lasting. So we have to kind of take that with a grain of salt in terms of overall, and yeah.
Definitely, and you're absolutely right. So this study was limited in several ways. One is that first off, we were only using mild COVID patients, and so if someone had been hospitalized, they were not part of this data set, and so that was one limitation. The other limitation was that we were looking at basically patients only within the first 2 months after they developed COVID. So this was still very, very quickly after that. And then lastly, we only had 46 patients in that cohort from start to finish. And so there were several limitations. I think that what we were able to see, though, is that there was consistently one thing that is very, very clear, which is reduced telomere length. Telomere shortening was something we saw in this study and has been now replicated, I think, in several other different studies. And so in addition to that, I think that most of the age-related change we saw was probably due to the change in immune cell subsets. And so this gets a little bit complicated nature, but as I mentioned, every cell in your body has a different epigenetic expression, and that includes all the different cells in your blood. And so sometimes if we see changes in those immune cell subsets, we might get age changes, which are not really age changes, but just changes in the cells that we're measuring.
Well,
Ryan, what we thought happened here.
My comment on top of Dr. Carter's comment, and also what you're talking about is, there's an old adage: what doesn't kill you makes you stronger. Mm-hmm. And a fever, just like hypothermia treatment, can be a very beneficial thing overall in terms of reducing your infectious burden across a broad array. And then, of course, that's going to have a profound effect on how your innate immune response is, what your innate immune response is. So I always titrate back to the infection. That's why I recommend you take a look at that Paul Ewald book. So like these immune cells go up for a reason, and it's almost never inflammation. The inflammation is a partner to immunity, and oftentimes it is immunity. So there's something underlying it. So anything that kind of reduces these burdens of infection that lead to a change in the immune cells, in my opinion, will have a positive effect on your analytics.
Yeah, definitely. And that's why I think our next study is going to be looking at other types of vaccines and viral responses. The group we're working at with Cornell is an immunology department, which really specializes in the epigenetics of viral infections. And so we're really excited to do some things with them. But I think the one consistent thing we saw is definitively COVID reduces telomeres, and it definitely has a differential response according to age, which probably suggests that the immune system's ability to mount a response or to correct correct from some of that stress, right? Like you mentioned with hyperthermia or even hypothermia, those periods of stress where your body can adapt are great if your body can adapt. But if your body can't adapt, they can be actually detrimental. I think that's sort of what we were picking up with some of those changes. And so again, more work needs to be done. But again, we're starting to figure out how some of these things affect us in our aging rates. And so, just to sort of wrap this up, we're doing a lot of other trials on things like senolytics, which can reduce your burden of senescent cells and those inflammatory cells. And so we did that with a combination of dasatinib and quercetin, which we saw some really exciting data that we're hopefully publishing with Yale very, very soon, where we actually didn't see a whole lot of change with some of these epigenetic clocks, but we did see some change with some special developed clocks that are particularly measure burdens of senescence. And that's been a very hard thing to measure classically. And so we're really excited to roll out that biomarker as well. We're also looking at even things like supplemental treatment plans. We worked with Quicksilver to do sort of a 3-month detox program, which actually saw reversals in that rate of aging marker. And even now we're doing some things with, surgery centers like UCSF, where these biological age predictors can actually be predictive of surgery outcomes as well, particularly things like spinal surgery. And so now that we have really good ways to measure this, what we're really trying to do is to find out what things work and how they work, so that we can make recommendations on how to reverse this aging process. And by doing that, we think we have major impacts on health and disease. And so I won't go into all the trials that we're doing, but hopefully this has been a good introduction to the epigenetic age process, how we measure biological age, and then also how we anticipate using it in the future to treat aging as a primary cause of disease. And so if anyone has any questions, I'd love to answer it. You can also email me directly with Ryan at TruDiagnostic if you have any questions, but we'd love to open up for questions now as well.
Well, Ryan, I think that's excellent. And, Mendeleev didn't win the Nobel Prize, but he was a Russian that understood the commonality between certain elements and created the concept of periodicity. And that was in the mid-1800s. And it took us a long time to really sort of capture the field of chemistry and manipulate it for our benefit. And I think with the age of information, we'll probably see a much greater exponential growth in our knowledge and use of epigenetics. But I see epigenetics and the commonality and periodicity of the elements to be very common sort of base structures to this. Now that's a positive comment. I'm going to make a negative comment, not about you at all, but David Sinclair. I was in Boston when Christoph Westphal and Sinclair sold Sertris to GlaxoSmithKline for $728 million. And neither Sertris nor Glaxo could reproduce his work. So my approach on David Sinclair is he's a really good spokesperson and marketeer, but my comment is verify, then trust, and then verify again. So like if he's the only one in the world that's restored vision in mice, I'm not a believer until I see 2 or 3 other groups do that.
Definitely. And actually, so
right.
Dr. Sinclair is also coming out with a direct consumer brand called Tally Health, which I think is actually, taking a step backwards in some of these epigenetic age diagnostics, because they're using clocks which have been trained to chronological age. And so I would say that, his sirtuin work has definitely gathered a lot of criticism as of late. But I think that, again, the commercial aspect is definitely different than the scientific.
Well, what Sinclair said, and it's very difficult to find this quotation, but they look at the sirtuin as sort of an antioxidant process, and of course innate immunity is all oxidative. And I remember Sinclair saying that, sort of, this is a rough quote, antioxidant therapy actually hasn't worked out very well in anti-aging. And so he's not a dumb guy whatsoever. And of course, his bank account probably looks pretty good after owning a part of Sertris and closing for $728 million. But my favorite guy is John Ioannidis out of Stanford, who wrote that paper that 70% of published research is false. So it's not. But it's kind of like what Dr. Carter brought out. And Michael, you got a lot of kudos from our audience about the comments you made. And it's like study design has such a profound impact on
Right.
And Ryan, to your credit, you talked very clearly about needing many touch points, and the number of touch points that you offer in TruDiagnostics is off TruDiagnostic rather is off the charts, and that's going to prove to be the most valuable thing. It's the number of data points and the correlation thereof. That's why we're in the mess we're in. Everybody just looks at total cholesterol. It's
Right.
like one marker misinterpreted, and we're supposed to get healthy based on that.
And I will make an interjection, because like Ryan was saying, when I started out on this journey of anti-aging, yes, I did. Well, the main thing was telomere testing, and it showed some very positive results for me. And again, everyone on this call knows I take quite a number of supplements, but peptides are a key portion of that for a number of years. And again, I was pleased to see that my chronological age, I'm 60 now, but based on Ryan's company's results, my biological age was 51. And then again, but if Ryan gets a chance to, show some of the other results, I mean, there are a whole lot of parameters on there, but most people will be most interested in that. And of course, the rate of aging, and my rate of aging was at 0.8. So I'm actually aging slower than normal. So again, and I feel that way, but it's nice to actually have some edification of that based on, the way that I eat, eating mostly an anti-inflammatory diet. Of course, I'm gluten-free, dairy-free, all that stuff, working out, doing P90X, and, and taking a bunch of supplements, including peptides. So I think that was reassuring to me that I'm actually on the right path.
Yeah, definitely.
No question. Is your technology, someone is in Australia, is it going to have that kind of, because it's just a blood spot, correct? Or could be?
Right. Yeah. And the good news is, as well, is that these methylation marks are very stable, even at long durations. And so we can do that in Australia. I would recommend that if anyone has questions about international, definitely let me know, because shipping can always be a big consideration and an expensive one at that. And so I'm happy to try and work and make sure we can get some lower cost testing to anyone who's interested. So please feel free to email me, but it is going to be available in Australia.
And you said yesterday that sleep, and then you talked about some calorie restriction has a very big effect on it in terms of changing the outcomes.
So I saw that question from Steve and would love to address it, because there's actually a really good preprint study that was just released from a group at Harvard, which looks at transient stress mimetics, so things like surgery or pregnancy. And we know that those things are going to increase transiently these epigenetic age markers. So stress, in a variety of causes, including things like viral infection, can increase these transiently. But generally, lifestyle factors should not, or I should say, should not as much, because really a lot of those have been controlled for in designing the algorithms in the first place. And so we know that sleep deprivation, is one of those things that can negatively impact it, but it's a real biological signal of sleep deprivation. Unlike, I think, some of these transient stress, which are just really happening for a short period of time and then can be corrected. And so, and as related to talk about that calorie study, we do know that things like caloric restriction, or really, even amino acid restriction or methionine restriction, are things that improve this metric, and generally in a lot of animal studies tend to improve lifespan and health span through regulating the mTOR pathway, particularly inhibiting that mTOR pathway, which might be, some people think, is one of the major reasons that we age.
What's interesting, Ryan, is that you might be able to help us simplify medicine rather than complicate it, because medicine today in ICD-10 has 77,000 diagnostic codes. And 77,000, I can't count that high. Dr. Carter can, because his brain is working so well with all his peptides. But listening for Michael's comment. But anyway, we say, 90% of diseases are driven by 4 mechanisms. 1, it's nutrient density. 2, it's how well you absorb. Absorption studies are not well done in terms of knowing, based on the variety of different human species, human subjects, who absorbs iron well, who doesn't, but a lot of it has to do with the microbiome. But that's really, number 1 is high density. Number 2 is absorption of nutrients well, and usually it's the micronutrients that are the most important. Our third mechanism is what we call thrive versus survive, and a subset of that would be fight or flight. You're always in stress. Your body only has so many resources to allocate, and if you're taking energy away here, you can't, you can't manage something less significant over here. And then our fourth mechanism are the underappreciated subacute infections, usually which only take hold if any or a combination of the 3 are a little bit out of whack. And that's kind of the philosophy under which we conduct our program. And then, of course, you go with Dr. Carter and do deeper dives into each of these different segments. But it'd be fascinating to just start building from your data sort of mechanistic hierarchies.
Yeah. And I will say, I've only done a couple of these tests on patients, but one individual that I've been working with for probably about 5 years now, and an individual who's kind of very regimented like myself, taking a lot of peptides and so forth, but he's 75. And it was very interesting to see that his chronological age, 75, but the biological age that came back on TruDiagnostics was 55. So he was very, very happy with that. So again, like I said, I've only done a couple of these, but it is tracking with, kind of what, our overall philosophy is, anti-inflammatory diet, taking the right supplements, healing the gut, the whole thing that we always talk about.
It's in the mouth.
Yeah. So
basic things.
Right. So, but it was very interesting to see that it is tracking, at least at this point, from my own personal experience, that it is tracking very well with what Ryan's company is showing.
Definitely. And these things are always going to get better as well. And so, I think that's one thing I'd like to mention too, is that these clocks are going to get even better at being able to capture, multiple different aging mechanisms. But one of the beautiful parts about this is that by looking at what genes are up or down regulated, we can also get an idea of that mechanism, I think, which Dr. Lewis, I think you were sort of alluding to, is that hopefully we can get an idea of what genetic, predispositions are being up or down regulated. And therefore maybe some of the mechanisms by which this aging process is occurring. And I think that mechanistic action will be very, very helpful in doing things like even designing therapies,
exactly.
New drug development.
Exactly. Yeah. I mean, that's what we do. Our whole protocols are designed around, me of those 4, I know Dr. Carter is much more precise in the way he does things, but when I just work on those 4, usually people will circle back and say they've experienced improved health, and that's all we can ask for at this point.
Absolutely.
Perfect. Well, thank you all again so much for having me. I just want to say one more time, if anyone needs to contact me, they can reach me at Ryan at TruDiagnostic. But it's been a pleasure to speak with this group. I think that this is a very educated group, and it's always interesting to talk to like-minded people. So if there's any way that I can provide more information, please let me know. But thank you all again for having me.
Excellent, Ryan. Thank you. Thank you. We see the future. The future is here, folks. Have a good evening.
Thank you all so much. Have a good night. Appreciate it.
What's the cost?
So just contact me, because it is a physician, only test. So I'll get you all the information.
Yeah. Okay. Are there bundle tests?
No, they only offer one test at this point. I mean, but
Doris, for you, we'll bundle something. Trust me.
No, what's the one?
It may not be just a test.
Only one test for all of that?
Correct. It's one test for all of that. And the other thing, as I mentioned, in perpetuity, if we update the reports, you'll get all of those updates free of charge. So if new science comes out tomorrow and we're able to report on it, we absolutely will. So hopefully this will be hopefully a continual informative asset as we get better at learning this. And we're definitely going to do that. The next reports we'll have will be the smoking and drinking reports, IL-6 Z-reactive protein, TNF alpha reports, and then a senescence burden report. So those are what we're coming out with next, and not available now, but within the next few months will be.
Excellent.
Trust me, Doris, it's extremely reasonable for all of the tests that they offer.
There you go, Michael.
But how did you get involved?
Michael, you're hired.
Ryan, did you tell us that?
I'm sorry, can you repeat that question?
How did you get involved in all of this?
Yeah, so actually, as Dr. Carter mentioned, my background was in working with really innovative and unique sort of pharmaceutical ingredients, and so a lot of those in various stages of FDA approval. And one of the things we always wanted to know is we wanted more data, particularly on how it was affecting lifespan, and health span. What are the it takes many years to do a double-blind, placebo-controlled longitudinal trial, and so we were really excited for the application to look at how these things were affecting lifespan. And so, I was always paying attention to this metric, but in September of 2019, for the first time, they published the first interventional trial showing a reversal of these epigenetic age markers via a combination of medications, including growth hormone, metformin, and DHEA. And that was the first ever study where they showed a reversal of these markers. And the next day, I was in Dr. Horvath's office trying to learn more about this and seeing how we could get involved. And unfortunately, I think there wasn't really a good test in the market. They were looking at really only 800, 900 locations, really just providing a test and not doing, I would say, the development to look at even better versions of this. And so at that point, we decided to just we actually sold our pharmacy and then decided to do this entirely. And so it's a still very, very new field, but one that is absolutely progressing at a breakneck pace.
Yep. Good question, Doris. Okay, folks. Have a good evening. Thanks again, Ryan.
Thank you very much.
Good.